Hello everyone, I hope you are all doing well. My name is Suyash Dash, my mentor is Akshay Gopal Krishnan, and today we will be discussing enhancing vehicle safety, integrating audio and object detection systems. Now before I begin explaining my research process, I want to share with you a common scenario. I bet many of you in the audience has driven a car, especially at night. We have this red car right here, and let us assume it has object detection cameras. It is in the middle of the night. The red car looks like it wants to take a left turn. Okay, but we have this black car right here. The red car is not alone. And the red car thinks that the black car will stop, but I'm not sure because it is making a lot of noise. It's going at a fast speed. It's honking at the red car. The red car thinks it should be fine, so it's trying to make a left turn. It's still making a lot of noise to the black car. The object detection cameras are not picking up the black car for some reason. It keeps going and eventually it begins to crash. Now, let us go back into the animation and let us discuss why did the object detection cameras not see the black car, which couldn't initiate the emergency braking system? Well, one reason is that it's in the middle of the night. The black car is black, and in the middle of the night, it's hard to detect black objects. Especially since it's night, it has low visibility conditions, making the cameras harder to see different objects. And another reason is that if you can see right here, the black car is about to hit the red car in its blind spot. What do I mean by blind spot? It is a spot that not only passengers cannot see that area, but even it's hard for cameras in the front, back, or possibly even side to detect the car. And considering the low visibility conditions, of course the object detection cameras could not pick it up and it caused this collision. Now, is there a way to prevent this from happening? Specifically, is there a way to have the object detection cameras or even the car have enough confidence to detect hazardous objects even in low visibility conditions that could prevent this from happening? My research says yes to all those questions. Yes. Issues and necessity of innovative precaution. Challenges with current visual object detection systems. We talked about this. Inefficiency in low light, fog, and rain, as well as blind spots not detected. Personal incident demonstrating system failure. My father and I, we were driving in a high-end vehicle about to turn left until a loud approaching vehicle was coming straight towards us. And it was scary because the camera detection system was not able to detect the loud car since it was from our blind spot. So it couldn't detect, it didn't initiate the emergency braking system. We were lucky enough to avoid the incident, but was a near collision due to these problems. Then, importance of integrating audio detection with visual systems. This is important because, for example, if we use audio detection in the incident, it could have detected the loud car from afar due to it being loud. It could have helped no matter the poor visual condition. Need for innovative solutions to safety gaps. What is going on? Companies are not able to test autonomous vehicles on public roads. Why? Because it's causing collisions due to not enough good detection. We need to consider safety with technology. Then lastly, audio detection versus LiDAR. LiDAR is right here. Camera doesn't show that well, but shows better in LiDAR because it's able to show from a 2D to a 3D perspective using special camera filters. Why are we not able to use LiDAR? Because it's very expensive with time and in money. And if we want something to be mass produced and to be used for the safety of all, audio detection right here can be used. So it can be something considered for car companies. Examples of problems in challenging conditions. We talked about this right here. Here's one with blind spot. The issue, it's able to detect right here, but it's not able to detect that car. So it caused that collision. Here's another one. Nighttime, it's very dark. Couldn't see that car, and it hits right there. But the similarity between these two occurrences is that it projects loud sound right before the collision. So if there were audio detection cameras there, it could have avoided both collisions. Now, the possibilities, sound waves are great because when we produce sound waves, it bounces to buildings, rooms, whatever, and it can be displaced around the area. So we can use sound wave reflection to determine distance and location, which I'll explain later. Sound detection can be displaced around the car, front, side, rear. We can have it around, enhance situational awareness. Potential to measure distance and location. Now, I was able to do it using data analysis and such. It shows it's simple, but but it can be pushed further with our technology to measure the right distance and location. And then, like a bat's echolocation, bats are able to navigate into dark caverns. How do they avoid the obstacles? They project sound, it comes back to them, they can estimate how long it takes, and they're able to avoid any obstacles. And if bats can do it, we can do it on the street with cars. Now, platforms and libraries. Platform, I use Google Colab, and libraries, I use GitHub repositories, but most importantly, Hugging Face. PyTorch was very important because it made all my pre-existing trained models used for deep learning models, made them all work together, especially working audio and visual detection systems together. MoviePy. When I was using videos, I need to break them into frames so it could detect each frame and then bring it back into a video. How did I do that? MoviePy was there to help. Video processing and frame extraction, and then synchronize. What it means is just puts the audio with the visual data that I had and make it into a video result. Ultralytics, YOLO. This was my visual detection. It was efficient and accurate object detection when it could work. It didn't work in those videos. It will work in the images I'll show you later, but it didn't work that time. Here's one example of when it did work. Pedestrians, traffic light, and everything, it showed right there. So when it works, it does the job. Transformers and datasets. It took me time to find an audio model, but I was lucky to find Clap DETR from Hugging Face, and it was an advanced audio classification. Gave me the confidence in need because it had a lot of street trained models and detection of various audio events, which was great. Flowchart of research process. Research used a lot of sources to see what datasets and information would best begin the research. Then visual detection, right here, collected datasets, as I mentioned, YOLO and PyTorch to put into code. At first, did it on images to recognize, then I used bounding boxes with the name and the confidence level to make the recognition successful, as you can see right here. And then if you can see, it has the name and it has a confidence, 0.32, means 32% confident or sure. And then audio detection, use YouTube and AudioSet to gather vehicles and street noises. AudioSet was great because it had the sounds that I needed to test. Then I used GitHub TensorFlow and Librosa to show sound on the graph measured hertz per second. This was very important in sound, but especially in distance because I can use the spikes to determine whether it was gradually growing louder, which means a car or something could have hit me, and then use that to measure the distance. Merged together, I merged the video and audio code together, made them work together. Lastly, used Clap DETR to help with sound of the video, but then was able to make the result. Speaking of results, enhanced performance, improved detection, accuracy in low light, fog, and rain, able to estimate distance without visual detection, and effective audio classification with transformers. These video clips show system in action and real-world scenarios demonstrating improved safety and precaution. Same video, but right here shows the confidence says 0.8, 0.7 increase, and it said near when the sound was made. So could have worked on that. And then here, right here, 0.8 and everything. Near, it shows detected. So another result working. Future applications and benefits. Enhance safety in vehicles, not only autonomous, but regular vehicles because we want safety for all, as well as improve emergency braking systems. Then assistance for elderly and individuals with medical conditions. We want them to only be safe, but independent on the road. And then safer for both inside and outside the vehicle. Overall impact. What is the overall impact? Increased vehicle safety, of course, but then also not only contribution to public safety, but technology advancement. We have the potential for technology advancement. This research can do the job. And then future research directions. What I noticed, we need more audio detection algorithms. We have the potential, but we need more audio detection to make it work, make it possible, more trained models to be used, especially data sets. Other data sets we can use not only to know, but also to use to make it work together like I did with my research. for training and validation, and then potential for incorporating audio detection feature in automobile industry. Make automobile industries use the audio detection so it can be mass produced, used in all vehicles, and have safety for all. Thank you for listening to my presentation. My name is Suyash Dash,